Okay, hello everyone, and welcome to this week's Materials for Energy webinar from Energy Futures Lab. My name is Connor. I'm the Communications Manager at the Institute, and it's my pleasure to welcome today's speaker for this week's seminar. Pichamon Sirisinudomkit is a PhD student in the NanoHack group, that's Nano-Structured Hierarchical Assemblies and Composites group at the Department of Materials here at Imperial College. She joined Imperial in July 2017 after completing an M.Eng in chemical engineering at Kasetsart University in Thailand. Her work focuses on enhancing the electrochemical and mechanical properties of nanocarbon networks for energy storage applications, and she's going to speak about some of that research here today. The presentation will last around 30 minutes or so, and there will be an opportunity after that to ask questions. To do that, use the Q&A box, which you'll find on the right hand side of your screen. Just type your questions in there and we will come to them at the end. The webinar is being recorded, so you can submit your questions anonymously if you don't want your name to be read out. And of course, the recording will be made available on our YouTube channel afterwards. So with that, I'd like to hand over now to Pichamon for today's webinar, and it's over to you.
Hi, good afternoon, everyone. Hope you can hear me. My name is Pichamon. I'm a PhD student in Professor Milo Shepherd Group, and today I'm very happy to be here to present on my own research work, modify single-wall carbon nanotubes for new generations of energy storage applications. I hope you guys can see my slides.
Yep.
Yeah, so as you know that nowadays the demands in the energy consumption is really huge, and there's a lot of development in the electrical device like mobile phones, laptops, or electrical vehicles. And one important factor is how to improve the energy storage device to compete like the demands in the market. There's three huge types of the energy storage device in this field, which are the capacitors, electrochemical capacitor, also called the supercapacitor, and the batteries. These three types of the energy storage device have their pros and cons in their own properties. For example, the batteries have really high energy densities compared with these two energy storage device, but then they cannot compete in terms of the power density comparing with the supercapacitors and the capacitors itself. As you can see from the cycle lives as well, the battery have really low cycle lives compared to the supercapacitor due to their own decompositions of the material, as they use the chemical reactions to store the energies. While the electrochemical capacitors or capacitor only use like the physisorptions, or the supercapacitor also use the redox reactions, which is highly reversible. In this case, the ions can store charging and discharging repeatedly. So in that case, that's the reason why the lifetime of this supercapacitor is very high. However, the ideal type of energy storage device that we need in the market is how can we have the high energy density but also still preserve the power density at the same time. In that case, I'm looking forward to focusing on the supercapacitor itself, because definitely the supercapacitor have really high power density, while the battery cannot actually increase much in terms of power density due to the chemical reactions. So in this case, further study on the type of supercapacitor first. They have two types, mainly dividing by the mechanism that store the charges. So the first type, called electrical double layer capacitors, store the charge via the physisorptions. So this material for the electrochemical double layer capacitor have to have the high specific surface area and also good conductivity to induce the ion to store on the electrode surface. In this case, The materials that they mostly use is the carbon materials, such as the activated carbon, single-wall carbon nanotubes, or graphene. However, the theoretical capacitance of the carbon material is still low compared with the pseudo-capacitive materials that using the redox reactions to store the charge. But the good point of it is because they doesn't relate to any chemical reaction, then the ion that absorb and dissolve out of the electrode surface can redo it repeatedly. So they have a good cycling stability and very good rate capability, which induce to the higher power density. The pseudo-capacitor is really interested by the researcher who focusing on the higher energy densities. They have two mechanisms, which is the redox pseudo-capacitance and the intercalation pseudo-capacitance through the hybrid double layer oxides such as nickel hydroxide or cobalt hydroxide. However, because these kinds of material actually be able to decompose easily from time to time, so they lack in terms of the poor cyclic stabilities and the low rate capability. So to improving the energy density and preserve the power density at the same time, these two types need to be hybridized by mainly using the EDLC materials as the substrate and then forming or hybridizing the pseudo-capacitive materials on top of the surface of this EDLC. But before going to that step, the first thing that we need to do is modify and optimize the electrode for EDLC supercapacitor first. And in that case, I use the single-wall carbon nanotubes materials as the electrode materials. The reason is because they have a high conductivity, low mass densities, large specific surface area, and high mechanical strength, which is going to be suitable for both electrochemical performance and mechanical performance. And then in further to develop the hybridized supercapacitors, they can easily give like the functional life cycle to hybridize other pseudo-capacitive material on top of that surface. However, the problem of this material is the nature of itself have the high pi-pi interactions or the strong Institute van der Waals that can cause the restacking back and also make the single-wall carbon nanotube itself bundle to each other that lead to the lower specific surface area and causing the poorer electrochemical performance afterwards. The way to disperse the single-wall carbon nanotubes in the solution, normally in the industry, they use intense sonications or mechanical force. But these two methods can actually damage the structures of the swings, create the defects, and then lower the specific surface area and give the poorer conductivities. So in my research group, we study further on other approach, which is called the reductive chemistry. The reductive chemistry normally use the alkaline metal solutions to make the charging negative and positive charging in the system of the solutions. So in my case, I'm using the sodium naphthalide to create the negatively charged single-wall carbon nanotube solutions in the solvent. And the results have been studied through Adam Clancy's teams that this method can make the swing soluble easily in the solvent and also doesn't damage the swing structures. So to make it into the clearer picture, I made the single-wall carbon nanotube bucky paper with the same concentrations of the carbon but different approach. So the first one is called the reductive charging process. Using the dimethylacetamide as the solvent and charging with the sodium naphthalide as the reductive agent show that the bucky paper that forming out can have the well-connected structures and more individualized compared to the carbon single wall carbon nanotube Bucky paper via the bar sonication at the same carbon concentration that still have lots of bundle and the impurity bar on top of the surface. And further investigate to the huge factor that can impact to the electrochemical performance is the specific surface area. You can see that the nanotube by Bucky paper give a higher specific surface area, even though it's not actually huge different, like double value compared to the Sonicate Swin Bucky paper. But the more interesting thing is the pore size distribution, that the nanotube by Bucky paper give more uniform pore size, even though we doesn't use any Corsinger, but the Sonicate Swin Bucky paper actually have the random pore size distribution and including more micro pore size. And in the study, it showed that the pore size larger than 10 nanometer basically can be large enough to ignore the interactions between ions and the pore walls, which means the size of this pore can be huge enough to make the ion transportation improving, and for the micropore from the sonicated Swin Bucky paper can actually give the poorer ion transportation lead to the lower power density afterward in the electrochemical system. And in the conductivity values that measure through the 4-pi probe measurements, it showed that the nanotube by Bucky paper actually achieve a higher conductivity compared to other CNT-based Bucky paper, including the Sonicate Swin Bucky paper here, which prove that the high degree of the individualization is expected to increase the conductivity. Further investigate the mechanism to store the charge in the nanotube by Bucky paper. I perform the electrochemical measurement of the electrode itself in the 3 electrode measurement first before fabricate as the device to understand the mechanism between ions and electrode via cyclic voltammetry methods, and then also further investigate the resistance, internal resistance and charge transfer resistance by using the electrochemical impedance spectroscopy. So as you can see from the cyclic voltammetry curve in both lower scan rates and higher scan rates, it shows that both of them have the rectangular shapes of the EDLC behavior, which is coming from the single carbon nanotube nature itself, and the minor small redox peak, which come from the oxygen functional group. However, in terms of interpreting the capacitance, the area under curve of CV curve can present out how much capacitance you achieve. And in that case, both in the higher scan rate and lower scan rate show that the nanotube by Bucky paper give very better performance. And at the higher scan rate, you can see that the shape of the sonicated Swin Bucky paper CV curve have more resistive curve. And that's also referring to the low rate capabilities and higher resistance in the system that lead to the dropping significantly in the capacitance at the higher scan rate. Also, the interpolating to the Nyquist plot that measures through the EIS techniques show out that the internal resistance of the nanotube by Bucky paper have a much lower internal resistance compared to the sonicated Swin Bucky paper, which also have a good agreement with the conductivity that I showed it previously, due to the improving in the pore structures of the Swin Bucky paper through the reductive charging actually improve both internal resistance and the charge transfer resistance in this case. So after achieving a high electrical chemical capacitance in the 3 electrode system, then I further improving by fabricate it into the cell device. But in the cell device, we shouldn't only focus on improving the electrode itself, but we also need to optimize the overall device, especially the separator, because it's also another key factor to improve the volumetric and gravimetric performance. So in my own device, so in my full cell device, the nanotube by Bucky paper not only act as the electrode, but also the current collector. So in this case, we can remove other current collectors out. That means we can reduce the mass of the overall system, as the nanotube by Bucky paper is conductive enough and can behave as a current collector itself. And the bacterial nanocellulose aluminum separator is only in the thickness of 7 microns. So in general, the commercial separator, we have the thickness above 20 microns, but this one we reduce down to 7 microns. To be honest, the reducing the thickness in the separator is quite risky, because then you have to make sure that the mechanical strength of its own separator is enough to not making the thin separator broken in the middle of the cycle life, because that means you actually make the lower rate performance of its own device. But in this case, we can further investigate and comparing it with the conventional cellulose and show the better performance afterwards. So fabricating the cell device, I compared the different separator by using the conventional cellulose, comparing back with the BC nano papers. It shows out that at the low current density, basically the performance is almost similar, but then it shows it more obviously at the high applied current density, which generally in the commercial we need to apply at the high current density to be suitable for the electrical applications. So in that case, the BC separator actually show a better performance and give a better rate capabilities throughout very high capacitance up to 100 ampere gauge. And the charge transfer resistance actually drop a lot compared with the cellulose separator due to the lower thickness, like 10 times lower, 10 times thinner thickness. So that means the BC nano paper can actually improving both the reducing the resistive loss and also improving the power density afterwards. To further study on the cycle life of the device using the BC nano papers, I fabricated and run it in the galvanostatic charge discharge curves for over 50,000 cycles. It showed that they achieve very good Coulombic efficiency above 89%, 98% after 50,000 cycles, and also it shows out that it can maintain good stabilities and really good rate capabilities of the nanotube by Bucky paper as well. The capacitance retention surprisingly reaching to above 100% and reached to 112% after 50,000 cycles, which actually quite surprising. So we further investigate through the CV curves after 50,000 cycle of cycling stability test. It shows out that the oxygen redox peak at 0.4 is removing out, so that means they deoxygenate the functional group from time to time. But then there's a huge peak of redox peak, nearly 0 volts, which we further characterization to the XPS and the Raman spectroscopy techniques. So the XPS detect the surface functional group in both positive and negative electrodes, and the ID to IG ratios of the electrode is increasing compared with the original electrode before start cycling stability, which can confirm that there is the grafted of the functional group of the surface on top of our nanotube bucky paper on both sides. And in this case, can referring back the reason why the capacitance is increasing, because the surface functional group contribute to the pseudo-capacitive behavior in the system. After achieving the high performance in the aqueous system, the other way to improving the energy density, not only using the pseudo-capacitive material, but we can also playing around by changing the electrolyte. So using the ionic liquid can improve the potential window of the cell, and then that the reason why can increasing the energy densities. However, the thing that we have to know that the ionic liquid itself have the lower mobility, which can cause a higher internal resistance and charge transfer resistance in the system compared with the aqueous. But providing at like 3 ohms in the ESI and RCT still low in terms of the ionic liquid system. So which refers to the nanotube by bucky paper is very good in terms of the conductivity. The CV curve shows a butterfly shape here, which unlikely not similar to the aqueous system due to it showing the quantum capacitance contribution due to the nature of single wall carbon nanotube interact in the ionic liquids. And it's also shown out in the gonostatic charge discharge curve as well, that not perfectly triangular shape due to the quantum capacitance contributions. The increasing in the capacitance retentions after 1,000 cycles here can also confirm by the same reasons of increasing in capacitance of the device in aqueous electrolyte, which the surface functional group grafting on the surface. However, you can see that there is a drop after 10,000 cycles due to the decompositions of the nature of the ionic liquid and the operating voltage that is higher than aqueous system. But keep in mind that 81% capacitance retention in ionic liquid is still high, so that can also present that the single wall carbon nanotube via reductive charging agent can make the good stabilities after all. To comparing the performance with other CNT-based symmetric bucky papers in both gravimetric and volumetric performance, I plotting the Ragonnet plot by normalized by the mass and volume of electrode materials to compare. It shows out that both in 1 molar sulfuric acid and in the ionic liquid present a higher energy density and way better gravimetric power density and volumetric power densities compared with others cell device in the literatures. So come to the conclusion that the reductive charging with the sodium naphthalide actually successfully to individualize Swin's bucky paper and can avoid the sonications or ultra centrifusions that may destroy the structures of the Swin's bucky paper and reduce the properties of itself. And the BC nano paper provide a new simple and thinner separator which decrease the resistance loss and maximize the volumetric performance in the whole cell configurations. And this symmetric nanotube by bucky papers in both aqueous and ionic liquid actually achieve very high capacitance. And this method can also maybe use it to further easily to functionalize the energy and pseudo-capacitive materials on top of this Swin's bucky paper. So in that case, we can improving and further investigate more in the supercapacitor batteries in the futures. So that is for today, and I would like to thank you to my research group NanoHack, my professor, my supervisor, Professor Milo Schaffer, Dr. F. Kinney, and Dr. Nelia for giving me very helpful suggestions and comments, and also Dr. Kunyang Lee for providing the BC nano separator for using in these research studies. Thank you for your attention, and if you have any questions, feel free to ask me.